reliability, efficiency, integrity, and usability. Again, correctness, you're checking that every feature you're adding is simply working the way it's supposed to work in. And we talked about reliability and efficiency. So again, when it comes to the speed of execution, when it comes to the number of users, let's say, trying to access your own application at a time, this has to be well managed. And of course, usability, in a sense, has to be well managed, right? When people are trying to use the service, it has to be easy to use and it has to be well reflecting the features expected. All right, now comes to the revision part. We look into flexibility, testability, maintainability, right? So every feature that I add to my application has to be testable. Again, this is reflecting on the importance of unit testing and later integration testing. Now, flexibility, in a sense, your code is not hard-coded. We explained this before. So later on, if new updates comes in, this will simply be flexible to add. Maintainability in terms of changes. So again, how will you treat a new request of a change? Will your model actually easily approve it, or it will be a pitfall, let's say, and you will have to restructure and redesign everything from scratch? Portability, reusability, and interoperability. Again, these are very important concerns to transition aspects. So again, portability means what? Who remembers?
You can easily carry it.
Okay,
You can move it.
so among different devices, let's say, perfect. So your phone can give you the same access to an application like your laptop, let's say, like a smartwatch. Perfect. Reusability in a sense. Am I inventing the wheel every time?
No.
Or I'm still having a core of my system that I can grow, right? So this is reusability. Interoperability, it means we're targeting.
Changeable?
Okay, that's changeable, right? So here, interoperability means, again, we're supporting multiple browsers, right? And yeah, so for example, I can run it, let's say, on Google, Google Chrome. I try, let's say, later on Opera. I find the same application working in the same exact way, right? So there's no trade-off. So we look into that picture now. This is what we want to explain. We have a source code. We have a binary executable file. I'll talk about this in more details in a while. And then a final output that gets to be rendered on the screen for the end user. We will look into what happens in between now, okay? All right, now let me reflect quickly on things you're taking already in SE201, right? Have you started calculating the algorithms like the big O, the omega, these stuff? Nice. I'm not going to dig deeper here, okay? But the main idea is, why do we need this? So moving from design, which was the last phase, to real implementation, having code. Do I have to end up having the entire code ready to test the design itself?
No.
To make sure it's efficient or not?
The entire thing?
Yes. Like, can I test things on the design still before I start implementation?
No.
Nothing?
If you know the structure, then you can like predict.
Okay, nice. So the main idea behind building algorithms is what? Do you have to build the entire code?
No.
How did you do it so far? The idea, we call this what? Pseudocode, right? So this is how the algorithm is planned to work, right? What are the key steps I need to have, right? What are the possible conditions? How many loops you might end up having? Is it nested or not, right? So we do make use of these instructions to calculate the individual statement or instruction effort. Now this together can lead up to the total level of complexity, right? So you can calculate, okay, this is a big O of n, this is big O of n square, or I don't know, could be exponential at a certain point. So here, by having only the pseudocode, I can tell whether this design is good to go or it needs some efficient redesign, right? And this can actually help you now see why do we have these algorithms. So I can still do the same exact, get the same exact output using any of these 2 or 3 approaches, right? But again, what makes it different from one to one? It's the level of efficiency, right? So, have you taken recursion or not yet?
Yes.
So you're aware of what happens here?
Yeah.
So a method recall itself with a lower degree of a value, right? So if it's n, next time it's n minus 1, then n minus 2, and so on. Perfect. Now what's divide and conquer?
Where you divide them into different methods to do specific tasks.
Close. You haven't taken merge sort yet?
No.
Not yet. Okay, perfect. That's okay. So when I have, let's say, a list of numbers, okay, I give it to you, and I ask you to sort them for me in the least possible number of steps. How would you do it?
No.
Hmm? It would require loops, of course, yes. So the idea here, this is one approach only. We call this divide and conquer. Okay, so let's assume I have 100 elements. You start by dividing the set here into two halves. So one will be 50, one will be 50. Now the first 50, the one on left, you will start dividing it again into 25, 25. Then again in half. All the way till you reach only 2 elements. Is that easy to sort?
Yeah.
Yes, so I can tell if this is 4 and this is 3, I can easily swap these two, right? So divide till you reach the minimum possible level of elements, then conquer again. So you remerge it all the way up, okay? So this is one technique. We have also dynamic programming. I'm not sure if you heard of it. Anyone? What's dynamic programming?
You code in binary?
Oh, no. Okay, that's not going to be binary in that case. It will be over exponential. Okay. Okay, so dynamic programming in that sense of, for example, if I talk about AI applications and the way they work. So every time you're expecting possibly a whole new set of inputs, right? Something very unpredictable, right? And every time you need to run a specific level of heuristics, let's say, to know how to solve this problem, right? So we call it dynamic because we can't really expect or predict anything at any point of time. So it learns as it goes, right? And every possible output might be a whole different one compared to another one. Now we have the greedy algorithm, and I think you covered this. No? No, not yet? Okay. Type, let me tell you. You have a set of coins, okay? So I gave you, I'll give fictionary numbers, okay? So let's assume I give you 100 cents. I gave you 50 cents. I gave you 25 cents, okay? And let's assume this is, I don't know, I gave you 12 of this one. I gave you 50 of this one. I give you 100 of this, okay? Quantity-wise. Then, okay, so this is the value, this is the quantity, okay? Then I ask you, I need 12 pounds, let's say, okay? I need 120 pounds or dollars, okay. Now give me the least possible number of coins that can give me that value. How would you do it? Algorithm. I'm not asking for the final number. How would you solve this problem?
You take the coin with the greatest value.
Okay. You will take this one first?
Yeah.
Okay, perfect.
No, you can't do it.
Huh?
Actually, you can do 50, 25, and then 25 again.
So this one will give you how many in total? How many real or how many dollar or how many pound?
1,012.
Come?
1,200.
1,002?
It gives you the value.
120? Is it 120?
Yeah. Why? Where did 20?
Type. So this is equivalent to type.
Too much.
So how many would you take from this to fulfill the value?
One gets
It's
one.
40 or
You know what?
50.
Let me make it 10. Okay. Let me make it 10.
No one's talking about ounce.
Okay. Let's assume.
No, we're not converting it.
Okay. Let's do it with 10. 10.
Okay.
Don't
And then
convert.
So you
Don't
take the
convert.
50.
So I
Take
take what?
50 cents because you want the least quantity,
This is
right?
the quantity. Wait.
That's the quantity.
Yes.
That's the value.
That's the value. You take the
Okay.
number with the greatest value. Okay, you'd use them all up until you're done with that.
Hmm.
And you take the one with the greatest value again and use the
So what is the one with the greatest value? That was 100. So
So in this case, it's
It's
okay.
100, yeah.
When it's 100, use the 100, right?
So that's how many?
12 times 100.
Okay, so this
Okay,
is how
so you
many
have
in terms of
100
dollars?
Yeah.
Total
What
of
if
how
it's
many?
120. That is not.
120?
No, you don't do make it fun.
That's 1,000.
Okay.
Okay, that's cent, right?
Yeah, that's
That's
cents.
cent.
Yeah.
So how many?
So in cents to dollars, what's the?
So that's 12.
So can you repeat the question?
Okay, you confused me. Wait, hold on. But Karina, we make it in Saudi riyal عشان we don't get confused.
Keep the dollars.
It's okay.
كيف نسوي هلالات يعني؟
No,
Let
طيب.
it be cents.
No,
Let
no,
it be
all of
cents.
them are in Saudi riyal, okay?
Okay,
So
okay,
these are
perfect.
Saudi
Alright,
riyal.
alright.
All of them, okay? I have here, I don't know, 10, 20, 30.
This
Quantity
is
wise.
100 riyal bill.
So this is
Yeah.
100
Okay,
riyal,
perfect.
50 riyal, 25
Yeah.
riyals. And I need 250 riyal. How would you get it to me?
You do 200
and 150.
Okay, 200 bills and then 150. That's it.
Two of that 100
Two of the 100 and then one of the 50.
Yes.
and then one of the 50.
Yes.
What did you do now?
You took the greatest value.
Greatest value first.
Yeah,
Thank you.
greatest value.
That's why we call it
Smallest quantity.
greedy
Yeah,
approach.
exactly.
Okay. So when dealing with greedy approach, we try to look into what is the maximum possible probability that can make this problem less complex. Okay. So when you took this one first, you ended up with only 50, right? So you solve it how much in terms of percentage? You solve a big part of that problem, right?
Okay.
Now what remains could be easily taken from the remaining amounts. So again, here we used only 3 values, right?
Yeah.
But if I do it the other way around, if I only told you, okay, use this first, how many will you end up with?
10 maybe.
10.
6 total, right?
To make 100.
Yeah. Right? So instead of only 3, you made it cost 6, which is not
Which is
efficient.
not,
Right? Again, this is very simple example, but it describes how greedy approach usually works.
Which is not what?
Efficient. Now, brute force. What's brute force? Everyone, every possibility. So just try everything. Okay? So technically speaking, if we're talking about Google Maps, when you specify a source and a destination, does it only show you one route? No, right? So it gives you all possibilities, right? But then it tells you, okay, this is the most efficient one. It takes more or less time, right? So again, brute force, you put all algorithms, right? All possible ways to solve the problem. But again, it looks into the one that will make it the most efficient. And of course, there is the pack tracking algorithm. When we talk about search, let's say. So assuming that these numbers are there in a tree. You've taken trees, right? And let's assume these numbers from one hierarchy level to another, it is actually sorted in ascending order, okay? So if this value is 10, this value would be, let's say, 20, 30, 40, like this one has less value compared to next one. Now, if we are in node number 10, we're here now, okay? And let's assume this is level 10. And let's assume the value here I reached was 1,000, okay? Then I'm trying to search for 950. Do you get it all the way from up?
Start from the bottom.
So how many possible search you will make? How many possible comparison you will make if you start it from the very top? A lot. Depending on how many hierarchy nodes you're having, right? Now, if you try this from the bottom level, it might take you, let's say 2, 3, 4, 5, but then it's not going to be as worse as you start from top, right? So this is what we call pack tracking algorithm. So again, all of these algorithms are meant to tell you how to start developing, right? So you have the design from previous phase, you know the problem, you know how to solve it with a given set of code. How will you redesign it in a more efficient way, right? Again, all these problems could be done with any of these algorithms, but it might give you different efficiency rate at the very end. So that's what we try to do. We look into a chart similar to, what do we call this one? What does it, okay, what did we call it from last chapter?
Decision.
Condition?
Behavior.
Prototype?
Action.
Activity.
Activity diagram. Activity diagram is when you have these nodes, remember?
Yeah.
Decision nodes, fork nodes,
Yes.
and all of this. Okay, so I know how the pseudocode will be written, right? I know the flow chart of these actions, and I know what is the input and what is expected to be the output. Now, you can measure efficiency only using these data, your design and your pseudocode together, right? And every time you notice anything off, you can redesign and restructure this design again. Make sense? So, okay, last point before we start. We have here developers and programmers. So we might hear these two terminologies a lot. How different is a programmer from a developer? Anyone knows?
What is
The
the
programmer,
program?
yeah. The developer actually designs the structure. Or
Okay,
the-
developer design the structure.
Yeah.
Okay,
The developer is in charge of the
Hmm.
entire project as a whole. while
Okay.
The programmer is in charge of the code itself.
nice, you're close, very close.
Systems.
All right, so the programmer, he's someone who knows how to code in any given language, right? So whether it's C or Java or Python, if I'm given simply a laptop, I can design anything I want, right? And let's now get back to the unit parts. So I can design a sign-in page, right, in any language. Not necessarily writing the full code, right? I'm not interested in the full code. But I could only be working on 10 projects only to make the sign-in and the registration, let's say, modules across all in different languages. Here, developer is someone who is dedicated, so he works mostly for that project, right? So he works on the entire software systems. He design, he plan, he integrate, he maintain all the software projects that he works on. He manage databases even, all the connections, making sure that they can integrate together and work as single component, right? On the other side, that person, this one works mostly on translating logic. Okay? Building flowcharts, so design mostly, right? Requirements, algorithms. So they turn this into a working code using one or more programming language. Okay? So again, here we're not talking about full code level, just simple component. But here, this one works on the entire code. And for this, we came up with the top-down approach and the bottom-up approach. So again, how would you solve this problem? So do you want to break it down into simpler stages? Or you want to just start by examining data and existing systems? So sometimes I have already an existing system to reuse, right? In that case, it's bottom-up approach. We call this reverse engineering. So you look into this system, what are you missing? You start building on top of it, right?
Yeah.
Here, it's the opposite way around. We start from a big problem, we start dividing it into simpler ones, like in the divide and conquer approach, right? So again, this one is not usually delivering real world applications, but this one often used to deliver more feasible solutions. And again, most of the applications nowadays are made based on reusable components. So it would align well with the organizational goals and reduce the level of complexity. So these are just some examples of dynamic programming problems. So talking about dynamic, it means every time you're having new situation, right? So imagine like there is a person at a given location and he wants, let's say, to exit. All right, how many possible ways you can solve it in? Many. So if the person location was here and the exit is here, it's different from someone who is here and the exit is here, right? So with every new input, the algorithm itself will differ, right? Or the way you will solve it is going to be different. Okay. Second problem is Fibonacci. So again, we try here. I think you covered this one already. Okay. Again, I'm not here to tell you more technicalities. These are just examples of dynamic coding. Same, let's say, when trying to check the longest path. Okay, so will you make a second move, let's say, that goes over 3 or 2 as a weight? And so on. So in general, we try to split our own languages into categories, and I will talk about this in a while. But for now, you might have heard of these languages so far. JavaScript, anyone? PHP? Nice. TypeScript? Okay. C++, just tell me if you heard about it or not. Okay. Python, of course, you did already. Rust?
Yes.
Nice. Go?
Go.
You haven't? Okay, nice. C#?
Yeah.
Nice. So these are well-defined problems and people already know about it. They can solve it in different programming languages. So these are just types of languages that we can look into. I will talk about this one in more details later on. But for now, simple one to go with is these scripting languages like JavaScript, TypeScript. If you're even aware of Unreal Engine or other tools, they actually provide you scripting languages that are specific based on blocks instead of writing code. We have procedural when you look into things like when you look into the heap, let's say, or how, let's say, processes or methods are being called step by step. We have event-driven, which is something you're doing already in SE201. So what happens when this button is clicked, right? How the event listener will be activated, how the event will be queued, or it will work, let's say, in parallel inside a loop, or you will have event handler at the very end. So these are different types of programming. So we can end it with this example here today. You're all having smart devices.
Yes.
Right. Let me give you a very simple task to do here. So there are languages that if you tried searching for, you would never even hear of it before. I'm not sure if anyone here heard about the white space language. LOL code, chef code, cow code,
White
false code,
space, how
chicken
do they
code.
debug that?
They have their own compilers.
Rockstar.
They have, okay.
What do they say?
That's what I want from you now. So search, I want you now to open the browser.
على بالي روكستار is it that company?
Not necessarily, I mean, I have no idea. I have never used any of them.
Rockstar for the
So either pick from this list or pick anything else that seems to be weird to your ears, okay?
Okay.
So let me know what is that language, okay? Tell me why is it used? So is it used, let's say, for web development or mobile or, I don't know, games? Just tell me what kind of context it's used in. And tell me a short snippet, let's say, of how it works in syntax, okay? Take it from the internet, you don't have to write it yourself. So this is already on Moodle. You can submit this to a forum discussion.
What do you want? Can you
So again, tell me the name of the language. Give me a short snippet of how it looks in syntax, and tell me why is it used.
Okay.
So is it for web? Is it for mobile? Is it for what platform exactly? Okay.
Can we upload it on the? Or we do it now?
It's on the forum. It's on the forum. Okay. On Moodle.
When is the deadline?
Take your time. Tell them tonight. Okay.
Okay.
All right. Again, all these in-class activities are not mandatory. You can skip, but it's good to try. Okay. So this now introduces us to two concepts: source code and pipe code or binary code. So here we can see all commands are given in English-like syntax, right? Which is easy to read. So if I, sorry. So for example, if I get to see the F keyword or the while keyword or the exit keyword or the return keyword, they are meaningful to you as a human, right? So even without knowing coding, you can still read and write into that language. Now here, if I told you, let's type hello world in binary, is it easy to do? Well, believe it or not, this is how programming started. So here, there is a language that could be understood and perceived by a user, a human, and there is another one that's understood by a machine. We call this machine language, written entirely into binary, zeros and ones. Now, what you are writing here is being compiled to give you a machine language that the machine understands, right? So instead of you do it this way, which is going to be horrible with every new instruction, you write it in your own language, then it gets translated, then the machine also gets to perceive it and execute it. Make sense? So simply, this is the level of all languages you will see so far. We have the high-level language. Some of them could be scripting. We have middle level. We have assembly. We have machine code and binary code. So in general, this is like Java, Python, Perl, Shell. This one is like C, C++. Now, the output of this layer is what we know as source code, right? Now, this one here, assembly language, provides you something known as a bytecode, sometimes referred to as object code. Okay? Now, this layer provides what? Binary code, exactly. So which one is seen by the user? This one. Which one is seen by the machine? This one. Okay? So this is just a sample of how it looks like, from high level to assembly to machine language written purely in zeros and ones. I just want to explain this figure and then I'll stop. So here we have the high level language to the object code, right? So compiler is what? Compiler is the tool that turns your high-level language into object code. Again, object code is not something you read or understand. It's in between both. In between high-level and in between machine language, all right? Now, for the compiler to work and give you this layer, there is something inside it, we call it interpreter. Have you heard it?
Yes.
So interpreter reads your code line by line, okay? Now the final thing, the whole file is seen by the compiler, right? So the report that you get is by the compiler using the interpreter. Now once you're ready with the object code or the bytecode, there comes here the task of the linker to translate this object code into the binary code, okay? In modern IDEs, you don't really see this much. So if you use, let's say, Dr. Java, you get to see a compile button, you get to see a run button, and so on. And everyone can actually make a change and show you what happens in the back end. But nowadays, most of them are just integrated into a compiler class. So you don't get to see much of what happens inside. But again, you might reflect back on these. Ever heard of JavaC in your installations? Have you seen this? So which one do you think this is? Is it compiler or interpreter or linker?
Linker? Yeah, linker.
That's a compiler.
Oh.
See, compile.
How about JVM?
Java virtual machine.
Yes, what is that for?
Interpreter.
That's interpreter.
Yeah.
How about linker?
This is a linker.
What?
This is from object code to binary.
From object to binary. I'm sure you didn't hear of this before. Something similar to GNU, let's say. GNU linker. GNU. It's okay. It is something in the operating system. You will take this later. But for now, we don't see linker job much. But these two are active usually. JVM, we have to install it, right? Same for Java C. You will see even files installed on your device for this. So for now, just know this. This is your file written, let's say, in .java format. This will be a file. So after compilation, this file will be, let's say, in .class format, which indicates bytecode. Then this one here is the executable file, which is binary, which runs directly on the machine side. Okay? I'll stop it here and resume this inshallah next time. Do you have any questions? Sure.
Thank you, doctor.
Thank you, ladies. Have a great day.
Thank you.